All right, welcome. Today, we are tackling a massive question, one that really sits at the very heart of both artificial intelligence and mathematics. We're talking about the challenge of building a blueprint for rational thought itself. Okay, so let's just dive right in. How do you actually teach a machine, a chunk of silicon and circuits, to reason? How do you get it to follow a chain of logic, from a set of facts to a totally new, valid conclusion? This isn't just some programming puzzle. It's this deep philosophical and mathematical challenge that has had brilliant minds captivated for, almost a century now.
You see, to even get started, the pioneers in AI and logic knew they needed something absolutely fundamental. They needed a universal language. Not English, not French, not any human language, because those are full of ambiguity. No, they needed a language of pure logic, something perfectly precise, with zero room for misunderstanding, a true blueprint for reason.
And out of that incredible quest, we got the hero of our story today, first-order logic, or what we'll call FOL. It's this incredibly powerful and honestly surprisingly elegant system that became the solution to this exact problem.
And this quote from the source material just hits the nail on the head. It's not some obscure theoretical idea. It's the workhorse of automated reasoning. This is the real-world engine that does all the heavy lifting in countless intelligent systems.
And its impact is just everywhere. In AI, it's what gives us the formal structure to represent knowledge. In pure mathematics, it's the very language used to define fundamental axiomatic systems like set theory. And in computer science, it's the beating heart behind logic programming languages like Prolog. It's literally the foundation that even more advanced logical systems are built on top of.
So, how does it pull off this incredible precision? Well, the genius of first-order logic comes down to a really clever separation of powers. It splits the whole world of logic into two completely distinct parts: the language itself and what that language actually means.
And we call these two parts syntax and semantics. Think of it like this. Syntax is just the strict grammar of logic, the formal rules for how you can arrange symbols. It doesn't care what they mean. Semantics, on the other hand, is all about the meaning, the interpretation, the actual truth, the story that those symbols are telling about some world. The real power of FOL is how it keeps these two perfectly separate, but connected.
And the reliability of this whole system was proven, rock solid proven, by none other than Kurt Gödel with his famous completeness theorem. It showed that for FOL, the syntax and semantics align perfectly. Anything you can prove using just the grammar rules is guaranteed to be true in terms of its meaning. Now, it's really important not to confuse this with his more famous incompleteness theorems. Those showed that any system strong enough to describe arithmetic will always have true statements that it can't prove. The completeness theorem is about FOL's internal consistency. It's a truly watertight system. But, having a perfect language is only half the battle. We need a way for a computer to actually use it. We need an engine, something to automatically perform deductions and find proofs. That engine would be the real game changer for AI. And that engine has a name, the resolution principle. We have J.A. Robinson to thank for this one back in 1965. He's the one who turned FOL from this beautiful theory into a practical tool for computers. And its method is just brilliantly counterintuitive. It proves something is true by actively going out and hunting for a contradiction.
So think of it like a contradiction-seeking detective. Here's how it works. First, you feed the computer all the facts you know are true. Then, and this is the genius part, you add the complete opposite of what you're trying to prove. You basically tell the system, hey, let's just pretend for a minute that this thing is false. The computer then just starts churning through all the logic, looking for any kind of clash. And if it finds one, boom, it means your initial assumption had to be wrong, which means the thing you actually wanted to prove must be true.
And believe me, this isn't just a theory. This exact contradiction-seeking method is the real-world engine that powers logic programming languages like Prolog, which has been used for decades in AI and computational linguistics. It's the real deal. So, okay, we've got this nearly perfect, elegant, powerful system. It seems like we've found the key, right? The key to building an all-knowing machine. But there's a twist in the story. This incredible system has a profound and totally unavoidable limit. For all of its power, for all of its elegance, it just hits a wall, a fundamental limit that it simply can't get around.
That wall is called undecidability. What does that mean?
It means that for certain problems, no algorithm can ever exist that is guaranteed to stop and give you a clean yes or no answer. A program might just run forever, searching for a proof that doesn't exist because some questions are, quite literally, provably unsolvable. And this is not some rare little edge case. Oh no, FOL becomes undecidable in some of the most important areas you can imagine. Use its full, unrestricted power, you hit the wall. Try to reason about the basic properties of numbers, you hit the wall. Try to formalize the very foundations of mathematics and set theory. Yep, you hit that same hard wall of undecidability.
So what's the ultimate takeaway here? It's this: the original dream of a single, all-powerful reasoning machine, a program that could solve any problem you throw at it using just pure logic, well, it's impossible. The very laws of logic itself put a hard limit on what computation can ever hope to achieve.
And that leaves us with this final, really fascinating question to just chew on. If a system as pure and rigorous and perfect as first-order logic has these fundamental, unsolvable problems baked into its very nature, what does that really mean for the ultimate dream of artificial intelligence? What are the true limits of the minds that we're trying to build?